This is cholesterol biosynthesis as it pertains to the drug lovastatin. These are objectives: to discuss cholesterol's role in the body, discuss how lovastatin inhibits high cholesterol, and discuss if lovastatin undergoes any structural changes before becoming active in the body. Cholesterol is a steroid precursor. It's naturally synthesized by the body, and it's obtained. Its building blocks are obtained dietarily. It's a type of lipid with a hydroxyl group at the 3 position of the A ring, which is down in the bottom left of the molecule you see there. It's an essential component of basically all living cell membranes. It's synthesized primarily in the human liver, but to an extent the small intestine. It's a 27 carbon compound, which will become relevant momentarily. And it contributes to, as we all know, heart disease via a process called, or a condition called atherosclerosis, which is a thickening or hardening of the wall of the vasculature, and also contributing to an accumulation of plaque, which can lead to things like heart attacks and strokes from occlusion eventually. So step 1 is the synthesis of what's called isopentenyl pyrophosphate. It's an isoprene unit, and it's one of the building blocks of cholesterol. It takes place in the cytoplasm of the liver cell, and this begins with the formation of what's called 3-hydroxy-3-methylglutarol CoA from acetyl CoA. HMG CoA is then reduced by the catalyst HMG CoA reductase, which again will become more relevant as we go on, to form mevalonate, which is a intermediate on the mevalonate pathway on our way to convert or to construct a cholesterol molecule. Mevalonate converts to 3-phosphomevalonate, which then undergoes a 3-step conversion process, all of which consumes 1 ATP for a total of 3. Mevalonate converts to 5-phosphomevalonate. This is all the pathway. It then converts to 5-pyrophosphomevalonate, and then finally isopentyl pyrophosphate, which contains 5 carbons. This is sort of the beginning, but most relevant step of this pathway as it pertains to lovastatin. We see HMG CoA is reduced by HMG CoA reductase, the enzyme, to produce mevalonate. And then we have mevalonate there on the left again, which then converts to 5-phosphomevalonate and then 5-pyrophosphomevalonate. And then finally, we're left with our isopentenyl pyrophosphate molecule you see here. Step 2, once we have that product, is isopentenyl pyrophosphate converts to dimethylthioalyl pyrophosphate via catalyst called isopentenyl pyrophosphate isomerase. It's an isomerization reaction. Then one molecule, if you remember, 5 carbons of dimethylallyl pyrophosphate combines with one molecule of isopentenyl pyrophosphate to form geranyl pyrophosphate for a total of 10 carbons. And then one molecule of isopentenyl pyrophosphate 5 combines with one geranyl pyrophosphate to form farcinyl pyrophosphate, 15 carbon compound, so 5 plus 10. And then 2 molecules of farnesyl pyrophosphate condense to form squalene, so 15 plus 15. Squalene is therefore a 30 carbon isoprenoid. And we're almost there. This sort of visualization from the textbook of that step in the process with our product squalene at the bottom. We're basically layering or adding carbons on top of each other. Squalene is then converted to cholesterol in step 3. Squalene is cyclized into a tetracyclic shape to begin its conversion to cholesterol. This tetracyclic product consumes oxygen and NADPH to form squalene epoxide, which is kind of an intermediary. Squalene epoxide then converts to can be known as a protosterol cation. In the textbook, it's 2,3-oxidosqualene. Then converts to lanosterol, which is still a 30-carbon molecule. And to get to cholesterol from this state, we need to remove 3 carbons. You can see in the visualization from the textbook, the bottom molecule, the cholesterol, the bottom left where that fork used to be, is removed, and sort of middle bottom of the cholesterol, there's another carbon removed for a total of 3, leaving us with 27. And that brings us to lovastatin. Lovastatin treats high cholesterol by reversibly and competitively inhibiting that HMG CoA reductase enzyme, which prevents the synthesis of mevalonate from HMG CoA. Lovastatin on its own is kind of an inert drug, but it's hydrolyzed by the human body to create its active shape, active compound, which then allows it to competitively inhibit this process, leading to a reduction in the body's cholesterol, a reduction in LDLs, and then hopefully a reduction in cardiovascular risk. Thank you. Have a good night.